So we are now recording. This is Precalculus. We're gearing right up for our second virtual learning class together. All right. Everybody should be able to see the presentation now, yes? Very good. Excellent. Someone's Chromebook is not loading. Well, I hope he can get in when he can get in. The good thing is that this is being recorded and it will be uploaded. So if he does happen to miss it due to technical issues, it will still be available for him. So that's good to keep in mind. All right, it is 11:20. I do want to get started right on time. Just want to present you with a couple minutes. Hey, Robbie, coming on in. Just want to present you for a couple minutes with a little do now up in the top corner. You could probably see it right here. How would you find the area of that triangle? This is a good little callback to geometry. So just a quick little do now to get you started. Think about it. I'll give you a minute to think about it as people are still jumping on in, as people are still getting all set up here. How would you actually find the area of that triangle? I'll ask you for it in just about a minute from now. So think about it. Hello, Jenna just came on in, which is great. Yeah, it looks like we got mostly everybody here, which is fantastic. Good. I know tech issues can be annoying and difficult sometimes, but hopefully we're all kind of working them through. But again, just figure out another 30 seconds or so, how would you find the area of that triangle positioned in the top there? Good. Think about it, think about it, think about it. Okay. All right, excellent. Hopefully everybody's thinking about it. Hopefully everybody's processing it. Hopefully everybody's getting all set up, getting ready for some pre-calc. All right, good. We got another person that just jumped in, which is fantastic. Emily's coming on in. Perfect. Everybody's here. This is great. Just about everybody. Just about everybody. Adam, you made it. All right. Welcome. Welcome, welcome. All right, so I think our minute is just about up. It's like, yes, sir. Ready for some pre-calc. So am I. So let's get going. I think our minute's just about up. So how would you actually find the area of that triangle? I don't know if anybody wants to type it in chat or anyone wants to unmute their microphone and say it, but I want to hear from you, from somebody. How would you actually find the area of that triangle? Little geometry callback.
You do the height times the width, and then you divide it by 2.
Adam, you got it. You are on the ball, my friend. We got
yes,
one half base times height. Absolutely. You may have heard that from geometry, right? You might be remembering that from geometry. So to find the area of a triangle like that, the formula is typically 1/2 times base times height. You've probably used that, or width, or whatever you want to refer to it as. Totally fine. So in order to actually do that, I would say that the area of that triangle is 1/2 times the base of 13 times the height of 8. And so that area would come out to be, I have to use my illegal rectangle in order to use my calculator because I left my graphing calculator at school. Tragic. But we got 1/2 times 13 times 8, which comes out to be 52 square units. 52 square units, right? So that's just a little callback to geometry. When you're finding the area of a triangle, you just have to really do 1/2 base times height and go from there. So you might be like, well, is that all we're going to learn in pre-calc? Well, kind of. We are going to learn how to find the area of triangles, but the challenge is going to be now that the area of triangles is not just going to be given the base and given the height. What if I gave you a problem kind of like this and asked you to find the area? What if I gave you a problem kind of like this? I said, here's our triangle. We'll call it triangle A, B, C. And just something that you may have forgotten from geometry, remember that angles of triangles are typically labeled using uppercase letters, and the sides across from those angles are labeled using the matching lowercase letters. So for example, if this is triangle ABC, then this would be side A, this would be side B, and this would be side C. So just something you're aware of. I know in a lot of the problems that you're going to be faced with, it won't give you a diagram, and it'll just say in triangle ABC, side B is this, side A is this. So it's just important that you understand that relationship. Now, what if I told you that angle C was equal to 50 degrees? I also told you that this segment right here, side A, was 13, and I told you that side B was 6. And I asked you now to find the area of that triangle. Your instructions were find the area. Well, you may initially be like, ooh, 1/2 base times height. I got this. No problem. We can do it. But then you might think to yourself, wait a minute. 1/2 base times height. I don't have the height. I have the base, and I have this length here, but there is no height. However, what we can do is we can actually use our knowledge of trig, and we can go ahead and find the height of that triangle. I could drop down this little vertical line here to create the height. That line is called an altitude, by the way. And I could say, well, take a look at this little triangle right here. I have this 50-degree angle. I have this side of 6, and now I have an unknown height. What trig relationship could I use to link those three together? Well, I have an angle, I have its opposite side, and I have the hypotenuse across from the right angle, so I can use sine. I can say that the sine of 50 degrees should equal the opposite of h over the hypotenuse of 6. That tells us that 6 times the sine of 50 degrees should equal the height. And again, using my not approved for school virtual rectangle here, we're going to go ahead and do 6 times the sine of, we got 50, the sine of 50 times 6, and we get that our height is approximately 4.6. I'll round up to the nearest tenth. Our height is approximately 4.6. And now that I know that my height is approximately 4.6, we can now go ahead and do our traditional area formula of 1/2 base times height, where I can say now the area is, thank you, I appreciate that, Maddie, for letting me know that her internet's not working. Luckily, she can watch this after the fact if she needs to. So we're going to get that the area now is 1/2 times the base of 13 times the height of 4.6. And again, I'm going to do that on my little calculator here. We have 1/2 times 13 times 4.6, and I get the area is about 29.9 square units. Does everybody see how we can do that by just using sine? So even though we're not given the height directly, again, we could use our relationship of sine to find it. That now leads into a formula that we can actually use to help find the area of any triangle given two sides and an included angle. So I want to say right here, given two sides and an included angle. Included angle means that's the angle that's between them. The area of that triangle, is, we could say that's now that the area is 1/2, still comes from the 1/2 base times height. The base, which we can call A, because that's what it was here, right? We definitely use this value, right, of B. Like, how did we find the height? The height was found by B sine of C. Do you see that? That the height was found using B, which was the value of 6, times the sine of C. So our area formula is just 1/2 AB sine of C. Okay? And that's how that's a formula that you can use to find the area of any triangle if you're given the two sides and an included angle. You could say it's 1/2 times the two sides you're given, and then the sine of the included angle in the middle. All right, they may not be A, B, and C, they may be different letters, but that's the formula we'd use. So take a look at another example. If I happen to have something like this, right, I called this 4, say I call this 73 degrees, and I call this 7, well, now I could just go ahead and find the area of a triangle like that by saying that the area is 1/2 AB sine of C. So that means that the area would be 1/2 times your 4 times 7, your two sides for A and B, your two adjacent sides, and then times the sine of C, so times the sine of 73 degrees. Okay? And again, just showing you, I'm really mad that I don't have my calculator, but just showing you on my illegal rectangle here, we got 1/2, so 0.5 times 4 times 7, so that gives us 14, which you probably could have done in your head, times the sine of 73. So we got times 73, the sine of that, and that should be equal to about 13.3. Or 13.4, I'll round up. Square units. Good. Does that make sense to everybody, how that all works out? It's just a little quick area formula. All right. Sometimes you'll see these problems presented to you somewhat in reverse, where instead of saying, here's the two sides and here's the angle, it'll say, all right, well, the area is this. Can you find the actual angle, or can you find one of the missing sides? So take a look at an example kind of like this. If I said the area of triangle PQR is 15 centimeters squared, I also told you that P is equal to 5, Q is equal to 10, and I wanted you to now find angle R. Okay, like find the measure of angle R. Well, what I would do first is definitely start by drawing a picture. So I could definitely draw a picture here. We have our little triangle. We have, we'll call it, doesn't really matter where you put the letters. I'll have P, Q, R. Again, remember that your sides now have to be across from the labeled angles. So there's side P here. This would be side Q across from Q, and this would be side R across from R. It tells us that the area is 15, P is 5, so this is 5, Q is 10, this is 10, and we're trying to find what this is. So let's just go ahead and use our area formula. We could say that the area 15 is equal to, what is it, 1/2 AB sine C. So 1/2 times 5 times 10 times sine of C. Everybody see that? And now we can just go ahead and solve for the sine of C. I'll get 15 is equal to 25 sine of C. I can divide both sides by 25. 15 divided by 25, reducing by a factor of 5, is 3/5, right? 3/5 is equal to the sine of C. And now I could just go ahead and use sine inverse on both sides. So I can say we have the sine inverse of, oh, I got to do 3/5 first. 3/5, which is just 0.6. And then the sine inverse of that. And I get that C is 36.87. We'll just round up degrees. Does that make sense to everybody? Well, that's kind of only half the story, unfortunately, because although, yes, it is true that C could be 36.87 degrees, it's also true that, thinking back to our unit circle, the sine in both the first quadrant and the second quadrant is positive. Right? The sine of any angle in both the first and second quadrant is positive. So when you have something like this, there are actually two possibilities for what the angle could be, whether it's an acute triangle or an obtuse triangle, because it could still have these measurements but be an obtuse triangle, still fit the picture, and still work out. So this right here is your quadrant 1 answer. So this is your quadrant 1 answer. In order to find your quadrant 2 answer, all you have to do is just do 180 degrees minus this quadrant 1 answer, because, again, that's how you find reference angles, right? So I would say that our quadrant 2 answer, C could be 36.87, but C could also be 180 minus that 36.87, because that angle in the second quadrant will have the same sine value as that other angle in the first quadrant. So I could say now that C could also equal, let's see, 180 minus 36.87 is going to be what? 143 point, oh boy, 13, I think. If I do my mental math correct, yeah, we're good. 146.13 degrees. And that would now be our quadrant 2 answer. So a problem like this that's asking you what is this included angle actually equal to could have two possible answers. One answer is your quadrant 1. That's just what you'd get by doing the sine inverse. But remember, this angle in quadrant 2 has the same sine value as this one in quadrant 1. You just figure that out by doing 180 minus that, and that's how you get the second possibility for what that angle could be. Again, quadrant 1 would be if it were an acute triangle. Quadrant 2 would be if it were an obtuse triangle. Okay. Questions on that? All right. The last thing, or last couple things I want to show you on that is that you could certainly get this idea extended a little further and be faced with some problems that look a little scary at the onset, but are actually really just hybrids of this. So let's take a look at a problem like this. Ready? It's something that is like, it tries to be really tricky and really sneaky, and then you take a look at it and you're like, wait a minute, I can do that. So we got, what if I told you? Find the area of a regular, that means just a standard where all the sides and angles are the same, hexagon inscribed in a circle of radius 4. Okay? All that means is you have a hexagon, which, again, all the sides and angles are the same because it is regular, and that hexagon is inside a circle, or inscribed, entirely contained within a circle of radius 4. So I'm going to try to draw this to the best of my ability here. Here's a radius of 4. 1, 2, 3, 4. 1, 2, 3, 4. It's going to be difficult. 1, 2, 3, 4. Oh boy, and it's being recorded too. No pressure, right? Let's draw a nice, complete, oh boy, full circle of radius 4. We got it. Okay, now I'm going to try to draw a hexagon. We got a side up here. We got a side that comes here. Oh, jeez, this is hard. A side that comes here. A side that goes like this. Oh, that's not really my best work, but oh well, we're just going to have to deal with it. So that's our regular hexagon. That's really lopsided. Our regular hexagon inside of a circle with radius 4. So if you notice, this right here would have a radius of 4. Okay? Now, notice that this seems really tricky and it seems like something entirely different, but it's really not. Being a regular hexagon inscribed within this circle, you could actually split this up into 6 triangles. Does everybody see that? And all of these would be radius 4 because that's all the distance from the center to the outside. Does everybody see that? This would be 4, this would be 4, this would be 4, this would be 4. Again, if my picture was drawn way more accurately, you would be able to see that. And now look at what I have. I have a triangle with a side, another triangle. We'll focus on this triangle right up here. Another triangle with this side. And I have my included angle. Well, how do I know how big my included angle is? Well, we just split this circle, which is 360 degrees. We just split it up into 6 equal angles. What would each angle be, therefore? It would be your 360 degrees divided by 6, or in other words, 60 degrees. So each angle of that regular hexagon would be 60 degrees because it goes all the way around, and it's the same all the way around. Hopefully that makes sense to everybody. And so now I can find the area of this triangle using my sine formula that we just came up with, because we have 2 sides in the included angle, and then just multiply by 6 all the way around. So I can say that the area should be 1/2 times the 2 sides, A and B, 4 times 4, and then my included angle, sine of 60. And then I'm just going to take this answer at the very end and multiply by 6, because there are 6 of those individual triangles contained within this shape. Hopefully that makes sense to everybody, yes? Okay, good. So, again, if you have a question, just feel free to speak up and interrupt. That's no problem. So now we could just go ahead and, again, refer to our good old calculator to figure that out. Sine of 60, though, shouldn't really be any trouble, because the sine of 60 degrees is... Sine of 60 degrees is... Sine of 60 degrees is...
I don't know. What is it? Tell us.
You don't know what it is? Of course, you should know what it is. The sine of 60 degrees. No, not pi over 6. That's 30 degrees. That's the radian of 30 degrees. Oh, the unit circle? Come on. Do I need to sing Lincoln sing the unit circle song? Oh, gosh. Oh, gosh.
Rad 3 over 2.
Rad 3 over 2. There we go. That's what I like to hear.
Yes, sir.
Sine of 60 degrees, rad 3 over 2. So we got that the area is 4 times 4 is 16. Half of that is 8. So I have 8 times rad 3 over 2 times 6. And so I get that the area is 8 divided by 2 is 4. So I got 4 rad 3 times 6, which is now 24 rad 3. There we go. And that's square units. All right. Does that make sense to everybody? All right. Way to go with that sine of 60 degrees. I know it's been a long time. I know it's been a long time with our unit circle, but it's important not to forget it for reasons like this, because it's just going to show up in problems like these. All right, excellent. Let me give you one more type of problem, and then we'll call it a day. All right, so another problem very similar to this, where it looks like something completely different, but then you're like, wait a minute, we can just use our sine formula, is something that looks like this. If I said, you ready? Diagonals of a parallelogram. Oh yeah, good old geometry. I hope I spelled that right. Are 20 millimeters and 25 millimeters and intersect at a 50-degree angle. Find the area of the parallelogram. All right, there we go. So, again, a great thing to do, just like we did with the previous problem, is to draw a picture. We got our parallelogram, looks like this. You can remember it's sort of like two parallel lines like this, and then I kind of do that, and I kind of do that. There's my parallelogram. We have our diagonals. So the diagonals are the lines that go from the corner to corner. So here's my diagonal. Here's my diagonal. That picture came out way better than the previous one. We're saying that these diagonals have lengths of 20 and 25. I'll call this shorter one a length of 20, and this longer one, excuse me, a length of 25. So the question I have for you is, if this one has a length of 20, what would be the length from here to here and the length from here to here? Well, if you remember, going way back to, oh, we got Alejandro in the chat already. Bam, 10, absolutely. If you remember back to geometry, the diagonals do bisect each other, and so these are congruent and equal to each other. So those would be 10 each. If you have this one being 25, then this would be 12.5 and 12.5. Very good. Everybody's already in the chat. 12.5, bam, all over it. Guys are all over it. Adam with that one really fast. And now to find your 50-degree angle, well, it would probably make sense for the 50-degree angle based on my drawing to be the acute triangle, right? This would be an obtuse triangle. It's bigger than 90, so that's 50 degrees because these angles are now vertical from each other. And therefore, what would these two angles on the top and bottom be? If this is a 50-degree angle, remember, this has to be whatever's left over to get to 180 degrees or a straight line. So if this is 50 degrees, then this has to be, what? I believe 130 degrees. And this one also has to be 130 degrees. Because if you notice, that's what's going to give us, yeah, Adam's all over it. That's what's going to give us our 180-degree straight line, right? Going back to geometry, good terminology to use is a linear pair, going way back to geometry, right? And these angles are vertical from each other. So that now is my parallelogram structure. If you notice, I have two triangles that match each other, these small ones on the outside, small one on the outside, with side of 10, side of 12.5, included angle of 50. I have these two triangles on the top now that match each other, side of 12.5, side of 10, included angle of 130, and the bottom, side of 10, side of 12.5, included angle of 130. So really, to find the area of the outer triangles, or the left and right triangles, I can say that that area is, using our sine formula, 1/2 times 10 times 12.5 times the sine of 50, because those are the two sides in the included angle. And how many of those are there? Well, there's two of them. So we're going to take that and multiply it by 2, because you have this triangle here and you have this triangle here, right? Now you also have those two upper triangles, so you just add that now to, same deal, 1/2 of 10 times 12.5 times now the sine of 130. And again, there's two of them because that represents your triangle down here and your other triangle up here. Hopefully that makes sense to everybody how we set that up. And now it just becomes a matter of plug and chug into your calculator, right? Half of 10 is 5. Ready? I'll show you. I'll show you just one step at a time here on my, again, illegal device. We got half of 10 is 5, so 5 times 12.5 is 62.5. I now want to multiply that by the sine of 50, so I'm going to do 50 and sine. And what's that equal to? That's 47 point, we'll call it 47.9. Let's multiply that by 2, and we'll get about 95.6. So our top triangle's areas come out to be about 95.6. And we're just going to add that to the bottom one. So now let's do the bottom, where we got 1/2 times 10 is 5 again. 5 times 12.5 is that, times, let's do 130, and let's take the sine. And we get 47.9. This looks awfully familiar. Let's multiply that by 2 again, and we get 95.6 again. Huh. Weird. Interesting. Why do you think that's the case? Why do you think this triangle's area would be the same as this triangle's area? By the way, the answer to this problem, as you're thinking about that, would be just 95.6 plus 95.6 is, I know, wait just a darn minute here. Wait just a darn minute. What black magic sorcery is this? How did it happen that this triangle's area is the same as that triangle's area? Think about it. 95.6 times 2 is, we just get 191.2. And this is in millimeters, so square millimeters. Okay. Does anybody figure out why this triangle's area would be the same as this triangle's area? Curious, you can feel free to unmute yourself, or you can type it in chat, whichever you feel comfortable with. That's true, David. David says because it's a parallelogram, and that's absolutely right. Diagonals of a parallelogram split into 4 triangles with the same area. That's true. But what else is true about the angles themselves? Think about these interior angles. We have this 50 degrees, and we have this 130 degrees. Think of how they fit into the formula. What's true about these two things, do you think? What's true about those two things? That's true that they equal 180. That is true. That is true. But what else is important about them, specifically related to the sine? Specifically related to the sine. Any ideas? Any thoughts? They're in, Adam just said, they're in the first 2 quadrants. Yeah, absolutely they are. And what's true about their sine values? Well, we just saw that they are the same. The 130 and 50 degrees would have the same sine values if you take a look at your unit circle. So really, again, looking at the sine, right? 130 degrees would be somewhere around here. And 50 degrees would be somewhere around here, just over the 45-degree halfway mark. And those two angles are the same vertical distance above the x-axis. They would therefore have the same sine value. So you're really just doing the same calculation twice. It's exactly the same connection as what we said down here, where you have 2 potential values for those angles. It just so happens that, if you notice, our 2 potential values for that angle comes up in the same problem. So really, these are 4 of the same triangle. You could have just taken the one calculation and multiplied them by 4. But I wanted to show you doing it out separately so you really see, first of all, where this actually comes from. And second of all, make the connection that the sine of 50 and the sine of 130 are the same because 50 degrees is a reference angle of 130 degrees. That's what we talked about before. Okay? Cool. That takes us just up to the last minute of class. How about that? Does anybody have any questions as to what we talked about today? And while you're thinking of your questions, let me just say, again, one of the big takeaways from today is this formula, which is what's used to find the area of a triangle given 2 sides and an included angle. That's a big, big takeaway. All right. It's useful because in geometry, which you've probably done up here, like that problem would just use 1/2 base times height, but you're not always going to know what the height of the triangle is specifically. We can now use our knowledge of trig to figure that out. Okay, so we can look at a little example over here. We can go backwards, and remembering that when we go backwards, there are two possibilities, one in the first quadrant and one in the second quadrant. Again, that represents an acute triangle with these measurements and an obtuse triangle with these measurements. And then we can just extend that to some polygons here where they're really these triangle problems in disguise, because you can just break up these polygons into individual triangles and then go from there. All right. Good question. Alejandro said, are we just focusing on sine and not cosine? This formula just uses sine. We're going to see something a little bit down the road, probably a couple classes from now, called the law of cosines, which is a similar idea but using cosine. But this formula itself just uses sine. Good question. Good question. All right. So just to let you know, we are just about out of time. Next class, I do have an assignment posted for you. Please make sure you get that done in time for next class. I'll be happy to go over any questions that you have at the start of next class, and then we'll move into doing a couple more practice problems. Maybe we will get to the law of cosines next class. We'll have to see how the questions go. But again, please try it on your own. It is posted on Classroom. It's due on Monday. So other than that, I do hope you have a fantastic rest of your day. Please feel free to ask if you have any other questions. But thank you for your attention and focus today, and I will see you on Monday. Have a great weekend.